In today's series, we will be starting a new project on game engine development. You're watching Maivor. My name is Emil, and I hope you enjoy. I'm very excited to start this game engine series. It's a bit of a different approach to how I normally would go about writing software, or, for the limited time I've been making videos, try and make a video, I want to try something new that might be a bit better. And so, starting at the beginning, in terms of game engine development, I normally, in the past, when I was learning, my pure focus was on learning how to use OpenGL. And once I got that working, I just kept iterating on that, but never really got anywhere. And then I realized, that's because I'm trying to make a game engine without trying to make a game. And so I made a few games. And this worked for the most part, and I learned a lot. But then I came to the conclusion that there's a few weak areas that I never encountered when I was just learning OpenGL, when I started making games. And ironically enough, while just messing with rendering, I would render a single model, of PBR or cartoon style or whatever type of rendering I was trying out that day. And so only one model and a couple of textures. So when I made a game, I ended up with like a gigabyte's worth of assets, and I normally would have loaded them as is from disk, like raw PNG or OpenGL or Collada or object file or whatever, and then just load them into OpenGL buffers and so on and so on. This is not an option when you make an actual game. That's how I started. And I quickly ran into a kind of a big problem, and that was that the loading screen took like 60 seconds to load. And the solution is quite simple. You just, take the data and convert it into something that you would normally store in a buffer object, like a VBO or IBO and all of those things, and then store serialize that to disk. So when you go to load the asset, when the game opens, you immediately just have already all the data properly structured to just load it into OpenGL. This works, but there's a problem when you try making a loading screen, and that's the second problem. And that is that I don't have any multi-threading. I've never tried to do that with OpenGL before, and the loading screen would freeze and unfreeze after every asset was loaded. And assets still took chunks of time to load, because while a PNG might be a couple of kilobytes, when you save it out as raw pixels uncompressed, it will, go up megabytes. So the raw assets was like, 50 megabytes, but the actual, baked assets was a solid gigabytes worth of information. And the solution is to use some really fast compression algorithms. I tried implementing, and in the end I made all of those things work, but it was a very hack approach, and the engine just sort of felt like one big hack job. So I thought, it might be fun to go back and try to build a new engine, which, by the way, I call my engine Apogee, and focus on getting those two core concepts right, because I've got the rendering part reasonably under belt, understand the asset loading part of it, and with my new experiences, I learned a lot about multi-threading and asset loading and compression and storage and so on. This is some extremely complex topics. Well, it's how complex you want to make it, right? And what kind of trade-offs you wanna do. So, and that's where I started. There's another big problem that I experienced, and that is workflow. Having to bake the assets takes a long time. It could take a good 2 minutes to bake the assets, but then it loads in like 4 seconds when the game opens. So baking makes sense when you ship a game, but it's very painful to do while you're programming, because you change the line of code, open the game, quickly test it, close the game, edit the line of code, the run, change, run, change, debug, run, change type of loop. And that's painful, really painful if you have to wait 2 minutes between each build. So the solution to this is caching, and that's what I ended up doing. So the only time an asset had to be rebaked is when you change something. But I didn't implement caching on a individual asset level, but rather on a global level. So if you change a single asset, every asset gets rebaked. And that was just because of the intrinsic way I designed my asset system originally in that old implementation. And later on, when I tried to add baking in and so on, it just, the design wasn't there to facilitate that. And it also doesn't facilitate live reloading. Restarting the game every single time just to change a shader while working on shaders is painful. And it's not that hard to implement live loading with a watchdog. The same goes for models, or textures and so on and so on. So that's kind of another key element. Another problem I experienced was that the dependencies, I use Linux, and the tooling I used is designed to run on Linux, but the game itself, primarily shipped with Windows users. So, so I had to make some very dodgy hacks to still ship the Linux tools, even though it's a Windows install, and just not execute those parts, and so the dependencies would never fail. That's not good. So I completely want to separate the IDE, not IDE, the editor, like the game editor, the asset system, and the rendering and runtime elements. So when you ship a game, it only ships the elements that does the actual game logic and the rendering, and that's it. No asset system or no, in-game editor that gets shipped with the product. And to facilitate that, you have to separate them from day one. So that's where I was. And again, I'm going to probably regret this, but I'm going to start building an engine just for the sake of building it like I did originally when I was learning how to make game engines. And then later we can actually start building a game. I just want to first focus on getting all the core pieces of information where they need to be. Now, that being said, I thought I might show you where I started. I've been doing a bunch of experimentation with .NET 5's new source generator, and I was experimenting with some, in my main thing, I was keeping a log of things I wanted to try, and it's all over the place. But I started off by making a simple virtual file system. And the idea here is to have compression, have some kind of an onion layering, live reloading thing like Docker has, and to support multi-threading. And that's what I built here. So what this does is, the way you use it is like this. You scope a group, and so I decided to make it so that when you load a piece of information, everything stays on disk. And what the file system will do is, only when you scope a group, it will load the headers, the information about all the assets in that group. And then once you try to read a group, it will actually get loaded into memory. And this way, it doesn't have a large memory footprint, but it's a tad bit slower. And so that's why you cannot do this on a global asset level. And that's why we have scoping. So you put all the assets you think you're going to load at the same time. For example, say you have level 1 and you put all the assets for that level in one group. Then when you scope that group, it will prepare to load that group into memory, and then it's more efficient that way. And once you've done that, you can open and read an asset and read it out. To create the assets, you will simply scope a group and then add it, plus this is just a stream, any stream, plus an asset entry. And so this is how this works. And it uses compression. I'm using the, here we go, LZ4 compression algorithm. And it's pretty fast. It's a tad bit slow. It takes about 2.4 seconds-ish to compress a gigabyte of information, which is not bad. And I'm going to implement the individual asset caches for caching. So, only the thing I changed is going to have to get reintegrated into this file. And then for the reading, it's really fast. I think it was, my testing showed somewhere around 500 megabytes a second. So that's great. Waiting 2 seconds to read out your compressed data is great. And I get about half the compression ratio with models and images and sounds and so on. just for some tests I was doing from some assets from other game I made to test the ratios, which is great. Taking the asset size from 1 gigabyte to around 440 megabytes is quite worth it, and the performance of this system is faster than the original one, so I really like that. And the way it works is it's just a basic one. We're still going to iterate on it quite a bit. I also haven't made a way to change it, so I might restructure this file's layout to allow you to rewrite. So at the moment it's read-only. You can only write it once, and then it goes into read-only mode because everything is packed into memory to avoid fragmentation. So if I want to make it so you can go back afterwards and edit the contents of a file instead of regenerating the entire file, I would need to do something a little bit more file system-y with blocks and like a link, interweaved linked lists, something like that. Maybe we'll do that, I don't know. And the way it works is everything that gets written to disk or to the file implements this interface. So just read and write to a binary reader and writer. And the first thing is a header, and it just has a magic number, and then a group index offset that it reads, and that group index offset points to the group index offset structure in the binary file format, and that then simply writes out the count of the total entries of groups in this file, and then it writes the group itself, the group entry. The group entry is just a list of group entries, and then it has a flag, and that flag is whether it's compressed or not. It has a name, a count, and an offset. The name is the name of the group. For example, in this one, the group is called test, or you can make that level 1 or level 2 or whatever you want. Then we have a count, and the count describes how many entries this group, how many assets is in this group. And the offset describes where the asset, the group entry starts in the file itself, the offset. And then, so here we just read and write these informations using the binary readers and writers. Now looking at a group, this offset points to an asset index, and the asset index again just writes the count out and reads it when it reads, and then it does the actual list of asset entries. The asset entry contains a name, a processor, which will be an enum, but we're just going to serialize that as a new int, an offset, and a size. The processor will point to a list of strings that have the namespace and the class name of the actual code that baked this asset, and that will just allow you to later on, for the live reloading. The offset is the offset to the start of the raw assets binary information, the bytes of the file itself, and then the length. And the name, that's the name, as you might imagine. And then the way that gets written is we start off by, here we go, writing the header to the stream. Then we go through every asset and we check if it's compressed. If the asset is compressed, we get the current position of the stream, so how far along we're in the file. Then we write the compressed data to the stream using the compression algorithm, and then we get the length of the data and store that as the asset's size. We then, if it's not compressed, all we do is we set the position, get the length, and then just copy the data directly into the file stream. And finally, we set the offset to for the group index. So this, remember, the group index IDX refers to a group entry, I believe. The group entry, which is this e.write, is where we're going to write the actual asset index table, and the asset index table starts at the current position, and then we store that. Then once that's done, we store the group index offset to the current position, and then we write out the header, and then we will go back. So we written it out like that, but then remember we wrote the header originally at the top without the proper offset. It's just set to 0. But now we finally know what the actual group index offset is. So we set that, and then we rewrite it again, and then we set this to 0 and rewrite the header again with the new offset. And so that kind of just generates the binary file that you see. And that's how it writes. So as for reading, you just do the same thing in reverse, essentially. And what you do in reading is, if I can find it, here we go. It's very simple. We just get the stream, blah blah blah. Then we read the header, get out of the header the index offset, and then set it to the stream position and read that out. Then when you scope a group, if it's in reading mode, which is over here, if it's in reading mode, we will set it to a new asset index, get the first group with the same name, then get that group's offset, and then we will read the asset stream from that given offset of the asset index. So once we've read out the asset index, that will propagate this. So that will mean this .toList will work properly. And then when you try to read an asset, this is just the same thing, except it just encodes it to ASCII, but so we just have to look at the one. And the way it works is we check if it's compressed. If it's compressed, we set the position to the offset of the start of the raw binary file in the virtual file system. Then we use a memory stream, and in this case I'm not adding using tag around it because I'm going to return it, so it's your responsibility to dispose it. Then here I'm telling it to leave it open when we do dispose the LZ4 decode stream. And here I made a little, this is actually outdated. Yeah. Lol, it should be like this. Yeah, I made this into a helper method. There we go. So that should let's just make sure the tests still work. Yeah, so the tests still work. Everything is less than a millisecond to read, yes. And the checksum is there, good. Okay, so anyway, so this will just copy the decoded information into the memory stream, and then we return the memory stream. So that's what I was saying about a single asset gets loaded into memory, and not all the assets in a group to have a lower memory footprint. This is a bit slower, but, well, it's better than, loading a couple of gigabytes into memory for a few seconds while you load an OpenGL and then disposing it. Doing it this way, the footprint's a lot lower, and lower end hardware can keep up. It might take a bit longer, but it should be fine. And we're talking milliseconds here, like 200 milliseconds maximum, or 500 if you have really old hardware. And then the read stream, if it's not compressed, we just read it out directly without using a decode stream. So that's nice and simple. And yeah, so it's a very simple, this doesn't do anything. A very simple approach and a very simple start. And the next step for me would be to redesign this to enable the fragmented version of this file format, where if you wanted to change any given asset in a group, you can change it. It will be appended onto the end of the file, but the old asset remains, so it's fragmented and uses unnecessary space. But the advantage being, while I'm debugging, I can live change this without having to wait like, a minute or 2 minutes every single time. And when you actually do a release build, you generate the entire file from scratch. The other approach would be to so what we're doing here is we read open and read all text. If we had some kind of a table mapping these entries to real files on the file system of the operating system, then we could check with a watchdog when they change, and then rebake them on the fly, and then just insert them there. And that's why it's a virtual file system. And I think that's the approach I'm going to take, so that this simple virtual file system is the heart of our asset workload in terms of how we interact with the game to add new content or iterate content, and in terms of how I as a developer will go about accessing baked assets at runtime while working with the game itself. So, but before we can really do any of that, and why I stopped at this point, we need to start thinking about actually baking assets. So I think a good place to start would be to make a simple texture asset processor, and then just open up an OpenGL window and draw a quad with the texture just to make sure it's working, and then to build the asset pipeline around that. And I need to remember to take things like cube maps into account, where there's more than one texture for a single asset, because I always map bold my structures one asset file to one asset baked asset output, which is silly. And then once that works, we can start adding more assets. For example, I think I'm just going to use Collada, which has nice animation support, so that we can support animations. And then we'll probably add a simple obj loader. I don't know if I'm going to do OpenJX again like I did in the past to support that as well. I never really ended up using that, so we might skip that one. And yeah, so that's kind of where this is going to be heading towards, to get the whole asset pipeline built. Once that is done, we need to start thinking seriously about how I'm going to separate the the content generation and asset pipeline and level editor and all of that stuff from the runtime game itself. How am I going to approach that problem? Because that would mean, the ideal would be to have an in-game level editor that can easily be separated out. And approaching all of that's going to be an interesting challenge. So yeah, I think I'm going to start for the next episode. We're going to start with actual asset processing and baking and storage and the virtual file systems mounting and live reloading of those assets. Once that is working, I'm going to sit down and think about how to approach the whole separation problem, and then we can move forward from there. Thanks for watching, and if you did enjoy that, please do consider subscribing. And if you have any suggestions or ideas on how to approach any of the things I discussed, or if you have any questions, please feel free to ask them in the description, and see you next time.